Hi, I'm Maurizio. For those of you who don't know me, I work in the LangTools team, so I take care of the compiler implementation, but over the last few years I had fun with playing up with many Valhalla features, and today I'm going to talk about one of such features, which is Valhalla Reflection. You may wonder what has reflection has to do with Valhalla in the first place. As you have seen in today's talk that Brian gave, reflection is an important part when it comes to inspect dynamically the content of a class file. And if we are going to change the contents of those class file, well, we may as well better change reflection, because otherwise we won't be able to see those changes in the class file. As usual, as great as my slides are going to be, please don't make any business decision based on that. And let's start with a basic definition of what reflection is. And as with all definition, we'll just pull it off Wikipedia. So Wikipedia says that reflection is just a mechanism for inspecting classes, interfaces, fields, methods at runtime without knowing the methods of such interfaces, fields, and methods at compile time. Great. It also allows the instantiation of new objects and invocation of methods. The way I read this is I really parse this into two different blocks. I see one structural layer, which is basically what gives me access to the guts of a runtime type. So I can ask a class, I can get the members of a class. For a given member, such as a method, I can ask what are the parameter types of that method and such. But there is also another layer, which is operational reflection. The operational reflection is what allows me to actually call a method once I get my hands on it. So I have a Java language method, I want to call it. I have a class, I want to instantiate a new object. That's kind of what operational layer does for me. And you may now ask, well, why do I care? I am a JVM expert or a JVM guru, why do I care about reflection? Well, turns out that a few years ago we were discussing about implementing languages on top of the VM, and Charles has a very good blog entry about what are the main issues about trying to implement a language on top of the VM. And the main problem is really getting around the limitation of the handshake with invoke virtual and invoke statics. So there is way too much Java-based semantics built on top of those codes, and we want to get free of such assumptions. So yesterday's solution was simply to use reflection as a workaround, not to be overly restrained by Java semantics. But this was not a great solution because it was still too strict, because you had to have a real Java class with a real Java method on it, and it was not giving very great performances, right? Because you need to have boxing all over the place, and yeah, that kind of sucked. Today's solution is, of course, invoke dynamic 292. So I can have a much sharper tool in order to create method handles. Method handles have a sharp syntax, so I don't have any boxing. And what's even better is that the client can decide the linking logic. So I have a lot of flexibility and a lot of performances too, because the VM can see through the call site and can optimize it at will, essentially. So we don't need reflection anymore, right? Well, sort of. This is an API that you should all be familiar with. It's the method handle lookup API, which we have talked about before. And as you can see, if you look closer, there are a lot of classes inside, right? If you want to look a method, the owner of the method is going to be a class. But there's more. There are method type thingies. And what are those method types? Well, they are just a bunch of classes. You get a class for the return type, you get a bunch of classes for the parameter types, and that's how you describe a method signature. So the real and fundamental problem with reflection is that right now we are using reflection as an entry point for getting access into this wonderland of method handles features. And if we don't have a way to describe the signatures in which we are interested in, we don't have access to such world. So if you are implementing your own language and you want Java interoperability, you need a way to be able to speak about the signatures that can appear in a class file. And Valhalla, newsflash, is changing those signatures. So we need a way to be able to describe them. And that's kind of the angle that I'm taking in this talk. Of course, in order to understand better reflection, we need to see how reflection evolved over the last few years. And so we'll start from the very beginning when reflection was really simple with a very straightforward semantics. So if you're going to work with very simple classes, such as Java-lang string, there's not much to learn about reflection. When you have an instance, you just get the class, which represents that particular instance. Once you have a Java-lang class on your end, you can do a method lookup, such as in this case, where you look for the method called length, and then you can even call the method by calling invoke. You get some result, you can use the result however you like, and it's pretty much straightforward, right? Reflection is all based on this subtle assumption in which if you have a declaration, you have a unique type that comes from that declaration. And if you have a declaration, you also have a unique runtime type that comes from that particular declaration. And if you work under this sweet spot assumption, well, that's a pretty powerful illusion, because I can actually pretend that the domain of my source types is exactly the domain of runtime types. So I can basically use one in place of another. For example, if I look at the members of string reflectively, I will get the same members that I get when I press Control space in my IDE. And that's the same thing. And that's a pretty powerful abstraction. Of course, we know better, right? Source types are not runtime types, and a source type, in some sense, is less rich. The runtime type has more things, such as a class loader. So the compiler knows anything about the class loader, but of course, if you try to load the same class twice with different class loaders, guess what? You get two different Java-lang class out of it. And there are also some more subtle issues. For example, accessibility. The way in which the VM does access checking is different from the way in which the language does access checking. And for example, in this case, we have a package private superclass. We have a public subclass which inherits a method which is public called m, and then we try to call this method reflectively from a different package. And what happens here, if the compiler didn't do anything, we will get a straight illegal access error, because the VM is seeing an access from a different package straight into a method that is declared in a package private class. Well, but if you try to run this example, it actually works. Well, it works because Java-C is actually bridging the gap here, and it's inserting an accessibility bridge inside the class sub in order to have reflection to link with the method in the public class instead of the method in the package private class. And if you have a field, well, who cares? I don't want to know, right? This is just to, okay, there are corner cases everywhere. In most cases, reflection just works, right? Well, it works, but if you start piling up new and new features on top of this very basic use case, then things start to get a little bit more convoluted. So let's consider, for example, inner classes, right? Inner classes, how could they be? Well, they are all about letting you declare classes not only as top-level entities, but also as nested entities. Well, one thing, as you can see in the slide, is that then you have to worry about what means for an inner class to access a private member of an outer class, which wasn't allowed before. And what does the VM do about it? Nothing. Java-C completely removes and wipes out inner classes from the picture when you compile, right? So you get a bunch of top-level classes, the picture is completely flat, and of course Java-C will have to add more and more bridges in order to let you access that problematic private member. As you can see, we are still in a sort of sweet spot, but not so much, because right now, yes, there is still a single source type for a declaration, but the source type and the runtime are kind of, they have different properties. The source type has some notion of lexical and scoping, while the runtime type doesn't. The runtime type is just flat. And what does reflection do? Does reflection expose a flat view of classes, or does it expose a more structured view of classes? Well, it kind of does both. So at the very basic level, reflection is still the tool for getting access to a descriptor. So if your field has a type of an inner class, Reflection will give you an inner dollar something class for that. But at the same time, reflection will also expose you the declaration property that this inner class came from. So you can still ask reflection questions such as, give me your declaring class, give me your enclosing method, and stuff like that. And how is this implemented? Well, the JavaC compiler will need to add some extra attributes on the class file because things such as, for example, the modifier of an inner class are things that are not represented in the bytecode. So these are added back as bytecode attributes. And reflection, guess what? It reads the very same attributes, and then it kind of munches them and presents them in a way that the user can understand. And it kind of works. Well, until it doesn't. So these are generics. So we have turned our complexity knob a little bit. And now we have generic class declaration. A generic class declaration is just a class declaration with some type parameter. And type parameters are just types that I can use in the declaration wherever I like. And clients can define what is the binding for those type parameters. So I can have a box of integer, I can have a box of string, and from the perspective of the client, they are basically just the same, just with different type instantiation. What does the VM do for this particular construct? Again, nothing. JavaC will completely wipe out generics from the picture during compilation. This is called erasure. This is what Brian talked about earlier. And since the erased version of box here is lossy because it's using object instead of X, the compiler has to bridge the gap once again and insert synthetic cast at the use side, because otherwise the code won't verify. Because for example, when I call get on a box of integer, I'm getting back an object, and I'm expecting an integer, so I need a cast. What happened here is that we broke one leg of our diagram. There is no more a one-to-one mapping between a declaration and a source type. Now we have a single declaration that can lead to multiple source types. On the other hand, erasure comes to rescue because it still collapses all the possible source types into the same runtime artifact. So if I have box of string, box of integer, box of double, I don't care. They are all mapped back into the single box.class abstraction. But with reflection and generics, we are actually at a breakage point because with generics, reflection is starting to do some weird things. So since reflection wants to expose the generic information that is available at the time of declaration, so let's say that you have a generic superclass. The reflection will allow you to see that generic superclass as it was written in the source code, which means we now have a new hierarchy, which is called Java reflect type, which is used to represent any type that is representable in the signature attribute that was stuck there by JavaC. Why do we need the signature attribute? Again, for separate compilation. And again, reflection is kind of parsing that attribute and exposing that information back to user. How does this work? Well, so and so. As you can see, if I have a class called subbox, and the class has a superclass which is generic, I can ask the same information in two slightly different ways. I can ask, what is your superclass? And I get a row box. Or I can ask, what is your generic superclass? And I get back a box of string. Wow. And this is actually the #1 most exploited trick to fake reification. I think a lot of EE code uses this in order to fake some sort of type reification at runtime. This is not the end of the string, though, because in JDK8 we added type annotation. So you can annotate not only declaration, but also types. And the problem now is that class is both a type and a declaration. So if we add some method for getting annotation on the type abstraction, class will inherit it, and so class will become inherently ambiguous and could expose both type annotation and declaration annotation. That's just too messy. So what we did instead was to add yet another hierarchy called annotated type. And this hierarchy is basically just used to reflect information about type annotations. So now we have yet another accessor. We can ask the superclass, the generic superclass, and the annotated superclass. They are all different types and with different properties, but they are all there. And if you think it's just a superclass, you're wrong. It's not just about superclass, it's about super interfaces, it's about the type of a field, which can be generic, annotated, or whatever. So basically, we have a bunch of accessors spread almost everywhere across the core reflection API. So this is kind of the analogy, right? The poor car here is Java class, and we kept adding stuff on top of it until the car can barely move. And guess what? We are going to add new stuff on top of it, right? Because we have still to get to the Valhalla bits. Yeah, right. So with Valhalla, you can annotate a type variable with the any modifier, which means the type variable is anyfied. If a type variable is anyfied, the very cool thing, but also the bad thing, is that the type variable will actually stay available in the bytecode. So if you could take a look at the Java P output for this class file, you will actually see X's in there, which is actually pretty cool. And another difference is that if you have a specialization, like a box of int, that specialization will actually stay alive in the bytecode. Because the static compiler, like Java-C, knows that the type for box of int is going to remain sharp all the way down. And so if you call get, you're going to get an int back, not an object. And you don't need any boxing or any cast or whatever. Good. But what it means for our diagram is that we also broke the other arm of our, of the diagram, where basically now, if we have a single declaration, we also have multiple runtime types. And guess what? It's even worse, because the arity of the source types that can come from a single declaration is different from the arity of the runtime types that can come from the same declaration, because some types are erased, some other types are not. So we can have box of integer which is erased, and box of int is not erased. So go figure. And so there is a bunch of things that Valhalla Reflection need to think about. Of course, as we have seen, there is a bunch of new constant pool entries that are coming with Valhalla to represent pretty much all the information that can revolve around specialization. So we can express generic types, we can express generic arrays, type variables, and such in a structural way. And the first challenge of Valhalla-based reflection is to be able to expose information to such constant pool entries. Because if we don't, this information is going to show up in descriptors. If we are not able to reflect over this information, we are not able to, for example, look up a method handle that shows up this information. A second challenge is to actually provide access to the specialized metadata. So if I have a box of int, I may actually be interested in knowing that my box is being specialized with an int. That's something different from what I had before, where everything kind of went back into the same artifact. Now we have different artifacts, and I may want to know about the difference at runtime. There is also the question about what to do about legacy constructs, such as foo.class, foo.getClass. As Brian told us before, it's not clear whether such constructs refer to the template class, or the array specialization, or to something else. And last but not least, how the heck do we implement operational reflection in an efficient way? Because if you look at Java-lang reflect method, it has a single invoke API, and that API is boxing, because it's using object as parameter type, it's using object as a return type, so there's no way you can call a method reflectively on a box of int and not get boxing. So that's another problem that we have to face. The three goals that I'm going to set up to evaluate any kind of solution that I'm going to come up in the next few slides are basically easy of use. So I want an API that is very simple. And why does it have to be simple? Well, because reflection is simple. As we have seen, it started off from a very simple API where there were very few concepts to learn, and I'd like to keep it that way. Abstraction fidelity is the second requirement, so I want an API that remains true to the nature of the things that I'm going to reflect over. While with class, I can't really say the same thing, because class is trying to be all different things to all different people. And the third point is compatibility. So I want an API that is able to guarantee, to make some sort of guarantees about compatibility, so that I know that I can use these new entities also in a compatible fashion to operate with legacy APIs such as method handle, lookup, and such. Solution number one, of course, is the obvious solution of let's add more straws on our car, right? Let's double down on Java class. We'll just add a new specialized literal, like foo of int.species. We'll add a new method and object, of course, getSpecies. They will both return some form of class. And class will have somehow to return information about what is the actual parameter type for the specialization. That can be done either by having class implementing parameterized type or maybe just by subclassing class in some way. Well, class is final. Well, we'll figure out a way. But anyway, that's the idea. So we have a box of int. We can get the species for box of int, and then we can ask the species, what is your actual argument? OK, that works. And then we want to do a lookup. We want to look for the method called get. We can invoke the method. If you pay attention, the invocation will actually do boxing on the return value, which is undesirable because the whole point of Valhalla is to remove indirections. But it kind of works. It's easy to use, certainly. It is compatible, yes, because I'm still using Java class, but it really sucks in terms of kind of getting a nice representation for the abstraction of play here. So let's look for something that is a little bit cleaner in terms of modeling. And what other APIs do we have around in JDK? Well, another API is the source reflection API that was introduced in JDK 6. We have an API that is mainly targeted at compiler writers and annotation processors. So it's an API designed for reasoning about programming language elements, so source types, not runtime types. But it's a very flexible API. It's all defined in terms of interfaces, hence the mirror term. And since it's defined in terms of interfaces, you can even implement this API and provide an implementation for core reflection on top of this. And that's what j.l.model did. It's also a slightly more modern API, so the return values, the aggregate values are returned as collection, not as arrays, which is a nice to have because then you can interoperate nicely with strings. Can we build Valhalla Reflection on top of this? I think we can. We can define a mapping, so a generic declaration will be some kind of element, a parameterized type will be some kind of mirror. We can also have some kind of compatibility layer so that we are able to map mirrors back into reflective objects. So for example, if I have a declared type, I can go back to a class. If I have a executable element, which is the Java model lingo for method, I can go back to a Java reflect method. If I have a variable element, I can go back to a field. And also, I will probably need to add a few mirrors for the types that are non-denotable in the source, like the raise token or the any for wildcards and such. What does the solution 2 looks like? Well, let's start off with the box of int. We get a mirror for that box. As we can see, we get a little bit of verbosity here because we have no language support for getting mirrors out of a box of int, but that doesn't bother me at this point in time. We can get the type argument, we can print out the type argument, and then we have the lookup. What used to be a one-liner using core reflection, it now turned into a bloody nightmare, right? We have 5 lines of very thick code, and the biggest problem here is that we have to go back from a mirror to an element because, yes, this API is clean, but unfortunately, lookup is a function of a symbol or of an element, and it's not a function of a type. So if you have a mirror on your end, you have to go back to an element, and then to do the lookup from there, and then go back to the mirror. Well, and what's worse is that this API is overly general. So for example, things like filtering by name is not easy because this API represents names as interfaces. So there is a general name interface, and to do a name comparison, you have to call content equals. It doesn't really fly, right? So it's definitely a cleaner solution in terms of abstraction involved. You have a clean separation between declaration and types. It's compatible because we added an explicit compatibility layer on top of it. But what is really bad about this solution, I think, it's easy of use. We can't really sell this to the average programmer, I think. In core reflection, you just have a single abstraction. Here you have two, you have types and declarations, and you have constantly to go back and forth between the two. Even without lookup, for example, if you want to know the package of a class, you have to go back from the type to the declaration, because package is a function of the declaration, it's not a function of the type. So all sorts of tricks arise because of that distinction. So guess what? We have to come up with something new, right? And we have to create something from scratch. The basic idea that I'm going to use here is to try to play a trick on you and to convince you that I can use a single abstraction to model both declaration and types. How do I do that? Well, I can say that box of x is a declaration and box of int is a type. And this is nice. It's actually a story that has been exploited by C# Reflection, and I think it leads to a nice simplification of the user model, because now there's just one abstraction that you have to think and learn about. So this abstraction, the root of my hierarchy, is called runtime mirror. A runtime mirror is basically the API point that is able to represent whatever abstraction can appear at the bytecode level. So what you can see is that all mirrors are created through factory methods, and you have common operations such as kind query, type equality, subtyping, and such. And of course, type mirrors can support multiple accessor entry point. So this is our taxonomy. If we look here, these are all the descriptors that I can express today. They are all UTF-8. This is both valid for classes, arrays, and primitives. But if we look at Valhalla, we get a bunch of new stuff here. We get values, we get generic types, and all are represented in terms of new specialized constant pool entries. And the key here is that all that is representable at the constant pool level has an equivalent in terms of the runtime mirror API. Of course, we need to be able to support specialization, which means some of those mirrors are going to be specializable. When a mirror is specializable, a mirror will basically offer an extra API point to go back and forth the specialized representation and the base declaration representation. So if I have a box of x, I can ask box of x mirror to get me the specialized representation for box of int, and that will work. And I can also go back from box of int to box of x. Another important use case is, of course, member lookup, which we have seen has failed almost spectacularly with the Java Lang model API. So we need something a little bit better here. And the way I went around this is to provide explicit lookup classes. So in order to do a lookup, you have first to retrieve a lookup class. Once you have a lookup class, you can specify a set of custom filters, and then you get the result of this lookup. You can get the result in two ways. If you are interested in all the possible matches for your lookup, you call a method called findAll. If you are interested in a unique match, you call a method called findOrFail, which either will give you the unique match or will just throw an exception. So these are a few examples for lookup. If we have a mirror for box of x, we can look, for example, for all the fields, and that works. Or if we are interested in a particular method, for example, we can get a method lookup, we can filter by name and specify get, and filter by return type and say, okay, the return type has to be the mirror for x. And then I can call findOrFail, and that works. Everything is declarative in this API, so there is no hardwired default like in core reflection, where, for example, if you call getDeclare members, get declare methods, you get only the methods declared in that specific class, but if you call get methods, you get all the publicly inherited methods that have been declared by either yourself or any superclass. Here you can decide how much stuff you want in your lookup. Of course, doing strict lookup with generic methods is a little bit of a pain because, as you can see from the slide, generic methods can introduce their own type variables. And if I'm going to do a lookup, looking at this from a client perspective, if I'm going to have to match this generic method, how the heck do I specify the signature for that method? Because I don't know about that type variable ahead of time, right? So the way Brian came up with a nice idea about this, which is, well, let's just add a new filter method which accept a lambda. So I can pass a lambda. The lambda takes in the type variables declaring the generic method that I'm about to kind of evaluate for a match, and it spits out the potential signature that I want to match against. So in this particular example, the lambda will return the parameter list that contains z, essentially, where z is the input of the lambda expression. And of course, it wouldn't be a reflection API if we didn't have some sort of operational feature, right? So we need to have a way for calling methods, create new instances, and how does this API go about that? Well, it doesn't. It really doesn't offer any support for operational reflection other than allowing you to project these new mirrors into abstractions that already exist. So for example, if you have a class mirror, you can go back to a Java class. If you have a method mirror, you can go back to a Java reflect method. And you do this by calling the special reflect method. The trick about the reflect method is that you can only call it if the underlying mirror is type variable free. So it must correspond to some type that is representable at runtime. If you have some type variables in there, it won't work. It will throw an exception because there's no live type that exists in the VM if you have type variables in there. You can also project these mirrors into something different. So for example, if you have a Java reflect method, you can project it to a method handle. And that actually is a nice solution because it gives us an answer for how do I do operational reflection on specialized classes. Because if I get a method handle, I don't have to use the same API for all the calls. I just create a specialized method handle for that. And that's going to work without boxing. This is how the last solution is going to look like. So I have a box of int. I can get the mirror for box of int through my factory. Of course, again, this is very verbose because I don't have any language support for it, but that's fine. Then I can specialize the box of x mirror with int and get a box of int. Then I can inspect the parameters. And as you can see, the lookup now got a lot better. I can just get a lookup method and then filter by name and then call find or fail. I get my hands on the method, and then I can project it back to a reflective method and call it, or I can project it back to a method handle. You have a question?
Yeah, I think you have a minor error. So the mirror from user class.
Can you repeat, sorry?
I mean, the runtime mirror for
Yeah.
from
Oh, right, yeah. There's an obvious mistake here. Yeah, it should be int.class. Yeah, sorry. Yeah, the question was, yeah, so go ahead.
What's the return type of get type arguments?
It returns a list of runtime mirrors.
So any type argument is represented as a, I mean, type parameter represented as a runtime mirror.
Yeah, yeah. And this is actually relatively easy to use. There is just one abstraction, which is runtime mirror. Yes, we have some subclasses like array mirror, class mirror, and primitive mirror, value mirror, and they may not even get it to the final stage, but there is still a main entry point to this API. I like this API because it remains true to what its goal is, which is to be able to remain true to what's available in the bytecode. So if you have some bytecode descriptor, you have a mirror for it, and you have a way to express the mirror for it. And it's also compatible because we can always project these things back into reflective objects, so we can still create a mirror for box of int and then convert it back to a class, and then pass that class to the method and the lookup API and be fine with it. Of course, there are several open issues. This is just the start. For example, there are a few hiccups around generic method translation. As Brian showed us this morning, generic methods are translated as inner classes. And currently, this is the only place in the new API where we kind of fake and fall back into the same bad tricks that traditional reflection does. So we kind of try to hide the inner class from the user, and that bites us back, because when we get a reflective object for the generic method, we get something that doesn't exactly have the same properties that the user expects. But we can probably put some patch on it in some way. Of course, I didn't even cover packages or modules. For packages, I don't even know whether something is needed. They are kind of a leaky abstraction in the Java line package API. Maybe a string is just as fine, and maybe we don't even want to expose the string. If you are interested in the package, you just map the class mirror back to a Java line class, and you get the package from there. Modules could be a similar problem. I didn't speak a lot about integrating source reflection and runtime reflection, but now, if we have two APIs which kind of do the same thing, wouldn't it be nice if we had a unified way to access to those API from the language? So we could have, for example, a way to have a type token, to extract a type token out of any expression in the Java language, and then to project this type into either a runtime type through erasure, or back to a source reflection type mirror all element API point. Of course, we are going to need language integration because we are not really too much into creating mirrors through factories. It's just too verbose for the main user. So, and that kind of ties with VM support. So what is the support that VM is gonna give us? I'd like to think that mirrors are the equivalent of today's Java line class. So there will be some sort of representation for the new constant pool entries in the VM. And maybe mirrors could be just the Java view of those VM internal representation. But it may be something else, of course. That's the end of the talk, really. There is a bunch of links. The first of the Valhalla repo, which contains an implementation for this API. Then there's a link for the Java doc for this new reflection API. And then there is a kind of the long version of this talk is a write-up that contains all the design decision behind the new reflection API and kind of the path that brought us here in the first place.